Hello and welcome, everyone. It's wonderful to see you here virtually at this year's Hope, and it's something entirely different to what we were beginning to organize, about a year ago, and I'm amazed and very happy that we've managed to do it. So first off, I'd like to thank the authors for submitting talks and Paul for agreeing to give an invited talk in a situation that was, well, definitely difficult for all of us. And I'd also very much like to thank our program committee for doing all the work that was necessary for this workshop. But from the organization side, I think I have to give huge thanks to the ICFP organizers, and in particular to the virtualization committee, without whose work, like, they have done the majority of the organization work for this workshop, even just by virtualizing the entire conference. And without their work, none of that would be possible. So I am very grateful. And most of all, I'm grateful to all of you who have come here to, join us at this virtual workshop in this new reality, I think, for all of us. So I think, I surely don't have much experience, neither in terms of hosting a virtual workshop, nor in terms of participating. So I think it will be a new and somewhat different experience for all of us. And I hope that we'll be able to have some interesting discussions, not just listen to the talks, but also recreate a workshop, a proper workshop experience, also in terms of having lively discussions. And hopefully we'll be able to do this today. The entire workshop will happen within this Zoom call, although as for ICFP, the chat is happening in the Clouder, so that's what we'll be using for questions and discussion. Well, discussion will happen here. So yeah, if there's any technical issues, as I'm sure there will be, please just let us know, and we'll try to work out what's happening and what's going wrong. So yeah, I think that just about sums it up. I'm very happy that we're here, and we have the first talk. And the first talk is the invited speaker of this year's Hope, and it's Paul Levy, whose work on call by push value has been incredibly important in the last years, in the recent years, to all of us working on effects, particularly in the higher order setup. So his work on call by push value has helped clear up the entire spectrum of effects and properly partition stuff into, properly partition our understanding of computation and evaluation, and has been a foundation of a lot of recent work in this area. So I'm very happy that Paul has agreed to give this invited talk today, and I know there's a lot of us who don't really know all that much about call by push value. So if you're one of those people who always wanted to know more about call by push value but were afraid to ask or didn't know who to ask, this talk, I think, will be great for you. So Paul, please.
Okay, thanks, Philip, and thanks, Ohad. It's a great honor to be invited to Hope 2020 as a, to give the keynote. And I hope I can see that the participants here who are experts in call by push value, and so I hope to have at least something for everyone, or at least something for someone. That will be an achievement. Okay. Anyway. So the outline is going to be 3 parts. So this is kind of an introduction to call by push value, but I also wanted something a little bit different to kind of show you some of the alternative options just partly as a way of kind of explaining why call by push value is set up the way it is set up by contrast, but also to discuss the possible advantages that they have. In the first part, I'm just going to be looking at pure lambda calculus. So the first part is higher order programming without effects. So I hope that's allowed in this workshop. And then the second part, we add effects, and that's what talk about, retrace the story that I always love to tell that leads to call by push value. Even if some of the details, quite a lot of details have to be left out, but at least I can give the outline. And then in part 3, we'll look at the variants. Okay. So what is call by push? Oh, my mouse is just right. Okay. What is call by push value? It's a fine-grained calculus of effects that has call by value and call by name subsumed into it. And the point that I always try to emphasize is that it's not something that I designed, right? It's something that I saw, and you can see it by looking at all of these semantics and putting them together, and you see they have this common structure of call by push value. So it's like a programming language that comes from the maths, if you think of it that way. But I think before we go into understanding call by push value, I think you have to start off understanding just pure lambda calculus. And I know that sounds like a funny thing to say because we all think we understand pure lambda calculus, but I just want to emphasize a few points that you may be only sort of vaguely aware of that help in the analysis of all the options. So let's start. When I say type lambda calculus, let's say that I mean the language with these types. I won't, in this talk, there won't be any base types, right? Just generated by these 5 operations. If you like things to be infinitary, you can also put in countable sums and countable products. If that horrifies you, then you can leave the green part out. Okay, that's up to you. A program is just a Boolean term, and the result of evaluating a program doesn't depend on evaluation at all, because this is a pure language, right? So evaluation order doesn't matter for pure type lambda calculus. And this language has a theory. What is the theory? It consists of beta eta laws for all of the connectives. So not only beta and eta laws for function types, but the less familiar beta and eta laws for sum types, right? They're all there. And as a result of all of these beta and eta laws, you get a whole load of isomorphisms. I mean, I've just given one of them down here, associativity of plus, but there are lots of others, right? People have analyzed all the possibilities. Well, actually, without base types, there's not really anything to say. So one point I really want to make about this language is that there are 2 kinds of connectives. Other people have made the same point. I mean, this point has been made by many people in different ways. This is how the way I want to put it. So the sum connective has a reversible rule, which is leftist. What I mean by leftist, you see here, if you've got a term inhabiting this judgment and a term inhabiting this judgment, you can put them together to get a term inhabiting this judgment. And the A plus B appears on the left. So I call this a leftist rule. Okay? And also there's this correspondence between pairs of terms and terms, satisfies some naturality conditions. I won't go into that. That's a technical issue. But, also, some of you will be familiar with that, but it's not, I don't want to emphasize that. If we look at the function type, on the other hand, it's got a reversible rule, which is rightist. You see a term inhabiting this judgment corresponds to a term inhabiting this judgment. Everything is modulo beta eta, right? Again, there's a technical naturality condition. And if you think of the product connective, that's bipartisan because it's got a leftist reversible rule and also a rightist one. Okay? So you've got leftist connectives, rightist connectives, and bipartisan connectives. So when you formulate this language that we saw, type lambda calculus, you have some options. So one option, we could have said that we're going to have multi-array sum types, right? So that would be a primitive. That ternary sum would be a primitive. We could have said that we're going to have multi-array function type. So that's a ternary function type. That would be a primitive. These are options. Another option is when it comes to the product type, we could choose the elimination rule. We could either have pattern matching or we could have projection. But because we have the beta eta theory around, although there are many versions of type lambda calculus, and some of them you have the multi sum type, another one you don't, and so on. You have all these different versions, but it doesn't actually matter which version you take, because you have, for example, the ternary sum decomposes via the binary sum because of the beta eta law. The ternary function type decomposes into the unary function type. The two kinds of product types are isomorphic to each other. So we have many different versions, but they're all equivalent. So the first question I want to ask here is, what's the biggest among all these versions? So the biggest version would have the most general leftist connective and the most general rightist connective. So, so the most general leftist connective gives you what we call variant tuple types. So here's an example of a variant tuple type. You can see that we have a list of type. This one takes five types, and it produces another one, and we get something which, up to beta eta isomorphism, is the sum of products. So everybody in functional programming has heard of sums of products, right? They come up everywhere. Well, that's the most general leftist connective. These types, which I wouldn't say it is a sum of products, but it's isomorphic to a sum of products. So what's in this type? We have two kinds of variant tuples, right? In zero tuple and in one tuple. And if you have something of this type, you can case analyze it into the two possibilities and do something different in each case. So that's the most general leftist connective that you could put into a version of type lambda calculus. What's the most general rightist connective? That's the variant function type. So this one takes 7 types. This is a 7-array type constructor, takes 7 types and gives you a type which is isomorphic to a product of multi-array function types. So what's in this type? A variant function with 2 bodies. If you apply it in a 0 way to a pair of things, you get M. And if you apply it in a 1 way to a triple of things, you get M prime. So you see you have 2 ways of, if M has this type, you can apply it in 2 different ways. That's the variant function type. Okay, so we've had variant tuple types, variant function types. So among all of our family of versions of lambda calculus, remember they're all equivalent because of the beta eta theory, but the largest of these versions is what I call jumbo lambda calculus. So in jumbo lambda calculus, you can form general variant tuple types and general variant function types, right? You have here any family of sequences and any family of sequences together with another type. And you can show in a certain sense that these are the most general leftist and the most general rightist connected. So you know you're not missing anything. Here's the term syntax. I've got the introduction and elimination rule for the tuple, introduction and elimination for the functions. And I've also thrown in, just for convenience, the ability to bind several variables. You can express this using lambda in application. You can also express this using tuples and pattern match, right? But it's convenient to have it there as a primitive. Okay, so that's jumbo lambda calculus. It's the largest among our versions. Okay, so now I want to give operational semantics to our pure language. I've told you that it doesn't actually matter the difference. It will matter later in our story, but for the moment, it doesn't matter. The two, if you like, I mean, there are many ways of evaluating lambda calculus, but there are 2 extremes. And I'm the kind of person who loves extremes, right? Opposite extremes, that works for me. So call by value is one extreme, call by name is the other extreme. Call by value, variables get bound to fully evaluated terms, which we call in that context values. Whereas in call by name, variables get bound to unevaluated terms. Nothing in between that. It's fully evaluated or unevaluated. And we have a judgment. This is a predicate about terms saying that V is a value in the call by value setting. And the syntax, you see, for example, in left of a value will only be a value if what's inside is a value. And that follows from this principle that variables only get bound to values. So in call by value, when you evaluate the terminals, that means when you stop evaluating, these are the closed values, right? Those are the terminals. Whereas in call by name, the terminals could be in left with complicated computation inside, right? So those are the basic principles of call by value and call by name. I've given, since Hope is inspired by the work of John Reynolds and his work on, he obviously did lots of amazing work. In particular, he really emphasized the importance of definitional interpreters. So this is, to my mind, this is the best way to really capture the operational semantics of a language as a starter. You can start from here and develop it in many ways, but the interpreter is the basic operational semantics of a language. Here's the call by value interpreter. I'm choosing to go left to right. So when I evaluate an application, I'm choosing to evaluate the operator first, get an answer out, then evaluate the argument, get an answer out, and then substitute. I could have done right to left. That would be a different alternative. In call by value, you've got to make a choice what order you're going to do that kind of thing. But the key thing is that you do evaluate the argument so that the thing that you're substituting is actually a value. Okay, so that's the call by value interpreter. And the call by name interpreter, you see the difference. For to evaluate application, you don't evaluate the argument. And importantly, when you're evaluating a pattern match, you don't evaluate under the constructor, right? That's just as important. And when you evaluate a let, you just make the binding, because let, after all, the point of let, remember, it just says that you're just defining variables. So in call by value, you would have to evaluate m and n prime. In call by name, you just substitute. Okay. So I've given you some examples of clauses, but of course you want to do this, you can do this for the whole of jumbo lambda calculus, right? In the case of call by value, you still decide to go from left to right. Okay, that's one kind of operational semantics. Another kind is the stack semantics. So this is a form of operational semantics that was made very precise by Felizen and Friedman, but lots of people have done something similar. I mean, the basic idea is very old. It goes back to Landin, or maybe even older. So CK stands for computation and stack. So any time in evaluation you have a computation and stack, and you start off with the stack being empty. And many authors will present this kind of operational semantics, we'll call K an evaluation context. So it's roughly the same thing as a stack, right? Okay, so I'll give you the example of call by name. You start off with evaluating a term. The stack starts off empty. This is the stack on the right. And let's say we have a pattern match. The first thing we want to evaluate is the thing that we're pattern matching. So the rest goes onto the stack, right? When 100 years later, this thing finally turns into in left, now you can take the appropriate thing off the stack and continue to evaluate. And you have similar rules for all the other things, application and so on. But that's the principle. Once you understand this example, then you can see how to adapt it for all the other things. And when you reach a terminal thing, like in left or a lambda abstraction, and you have nothing left on the stack, that's when you stop. Okay, so that's for call by name. For call by value, it's a little bit more tricky because you've got tuple. If you have tuples, a tuple can have many. You have to evaluate all the way in. So you need two kinds of configuration. You need a kind where you have a computation and a stack, and a different kind of configuration where you have a value in a stack. So in this case, you're working on the computation, and in this case, you're working on the stack. And you flip back and forth between the two kinds of configuration. That's the call by value. So it's a little bit more complicated because of the tuples. Okay, so we've shown operational semantics in two different ways, using an interpreter and using stacks. What comes next? You know, it's suspense for me because I can't remember what comes next until I see the slide. Okay, since stacks are another kind of term, they need a judgment, right? Everything, I mean, I love types, right? I'm sure you do too. So anything I see, I want to give it a typing judgment. So now that we have stacks, I want to give them a typing judgment. So K is going to say that this judgment means that K is a stack, possibly with 3 variables. In practice, when there won't be any, but you know, we like to have them there in the judgment. So gamma would give you the 3 variables. B would be the type of computation that K accompanies, and C is the type that's being evaluated. So K is, if you like, a stack going from B to C. If you think of K as an evaluation context, C is the overall type and B is the type of the whole. Okay, so that's what a stack term is. So again, we have this judgment, we add this to call by value, we add this to call by name so that we can type check the CK machine. Right, that's the end of pure lambda calculus. We've looked at the different versions, including the largest version I should have a summary slide. Well, let me tell you anyway. We summarize. We've seen the largest version is jumbo lambda calculus, but there are many smaller versions, and they're all equivalent. Then we had two kinds of operational semantics: interpreter and stack, for both call by value and call by name. So that actually means 4 different operational semantics overall. Now we're ready to begin the experiment. The experiment that gives rise to call by push values is that you start with pure type lambda calculus. Which version? Well, you can probably guess what I'm going to answer, but I have to justify it. So it's a question we have to discuss. And we're going to then add in an effect or some effects. And if you remember, I mean, Moji long ago gave an amazing list of all these different effects: errors, divergence, IO, memory, new names, changing the stack. In the call by value setting, the word a stack is a continuation. So that's synonymous in the call by value setting. Non-deterministic choices, probabilistic choices, all of these different effects. And of course, you can have more than one. So you take these effects, you build denotational models, and you analyze, right? That's the story. That's the basic experiment that you look at what you see. If that makes sense. You look at what you get. So to summarize our experiment, we start with a purely functional language, pure lambda calculus. We add imperative features, we throw it all in, we shake it all up, and we see what we get, right? On the face of it, it's a very strange thing to put together, because these are 2 very different kinds of language features, but that's what we're going to do. So here's, if you like, a summary of the outcome. The story so this is really the second part of this talk. The 3 talks is this story that leads to call by push value. So we start with call by value or call by name jumbo lambda calculus. I'll explain why jumbo. We can put in the stacks if we want. If we're using the interpreter, we don't need them, but if we're using the CK machine, we do. Call by value, decompose in 1 step. So if we look at a magnifying glass with call by value, we get fine-grained call by value. And if we look at these 2 with an even higher resolution, even stronger magnifying glass, we look very closely at the very fine-grained structure, we're going to see call by push value. Again, if you started with stacks, then you're going to have stacks at the end. But if you don't, then you won't, right? So you can have the blue stuff could be in or out according to your preference. That's the basic picture of effectful lambda calculi. Okay, what do I mean by adding effects? I just mean that we're just giving an instruction to the interpreter. That's all we do. We add to our language the ability to put a little side effect saying print hello, or crash with, halt with the error message, crash, right? So in this is for the errors, this is for printing. Those already 2 very simple effects, they illustrate a lot of things, right? You can see we've added another clause to the interpreter, which does what you expect. And these things happen at any type. We ignore the types, we just throw these in. Print C is a prefix that you can put onto any type. It's a algebraic effect, as we now call it, but yeah, it wasn't always called that. But okay, it's an algebraic effect. Right, quick exercises. I hope I'm not crammed too much into this. Anyway, just give you about 10 seconds. I'm not thinking during these 10 seconds. So now I have to think and embarrass myself. In call by value, you first of all evaluate the operand. So you print hello, that returns 4, and you're going to return 8. In call by name, you're going to get print hello 4 plus print hello 4. You evaluate, you're going to get print hello. It's going to print hello twice and return 8. Okay, what about this one? In call by value, you start by printing hello. You evaluate under the end right, so you're going to crash. So print hello and crash. Call by name, you're going to print hello, but you don't evaluate under the end right, and you return 5. Okay, that's quick exercises. Right, so we've got our languages. We've got call by value and call by name languages. We've added these effects. So what's going to happen? Which of our equations survive as observational equivalences? Which of our isomorphisms survive? Can we give a denotational semantics? And if we analyze the models that we get for all of these different effects, what patterns are we going to see? Yep. And we could do this for any version of type lambda calculus, right? I told you there are all these different versions. But the advantage of doing jumbo is that we cover all the possibilities. In particular, we're going to lose the beta eta theory. So the fact that I told you that everything was equivalent is no longer true. So it really matters to be as generous as possible so as to be sure that we're not missing anything. That's why we want to start with jumbo lambda calculus and not one of the other versions. Okay, let's take a look at what equations hold in call by value. So here's an example of a call by value equation. This is the eta law for a sum type, or a version of the eta law for sum type. So this says, basically this says that if you have a term m that uses z, then z has to be either in left or in right. So if you first of all pattern match it, it won't make any difference, right? That's the eta law for, and that's true in call by value. Z is a value, so it's either in left or in right. By the way, that's not a proof what I just said, but it's just an informal argument why this holds as an observational equivalence. And a similar reason, the isomorphisms for plus hold. If I wanted to be really precise, I could discuss what is meant by an isomorphism. So I had a paper, Contextual Isomorphisms, in PUPL 2017. If you want to find out more about what exactly I mean by an isomorphism. But the rough idea is you can go there and back and get back to where you started. So you get that in call by value. You don't get it in call by name. In call by name, you have the eta law for function types. This is pretty subtle. This thing m, maybe m crashes. This thing doesn't crash, it returns a function. But if you, in both cases, if you apply them to an argument, the only way you can evaluate something of function type in call by name in the context of a program is by applying it to something. And when you apply these two things, you get the same answer. So the fact that the eta law holds for function types in call by name is a subtle phenomenon, but it doesn't hold in call by value. And again, here's an example of the famous currying law, currying isomorphism. This holds in call by name as long as we use the correct choice of product, but it doesn't hold in call by value. Okay, remember this product is a special case of the variant function type. We've only got variant tuple type and variant function type. So there's a product which is a special case of the variant tuple type, and the product which is this one, which is a special case of the variant function type. Okay, in call by value, we have the nullary function type. Remember, we have multi-array function types present. One particularly important one is the nullary function type. In call by value, that's called a thunk type. We often use this abbreviation TA for this, and we write thunk m instead of the nullary lambda abstraction and force m instead of the nullary application. And thunks are really important in call by value programming because they're used to delay evaluation. Okay, so this is call by value. I'm starting to talk about call by value, right? I think we've moved into the next section. We'll talk about call by value. We have thunk types play a special role, and we can give denotational models for various effects, and then we analyze them. Right now, unfortunately, this is a high-level talk, so I can't now go off and spend a lot of time going through denotational semantics of call by value with exceptions, denotational semantics of call by value with printing, with cell generation. That's really important to see the structure. That's really helpful to see the structure. So you've got all of these different models. So you have to imagine now that we've got lots of different models. I just quickly prepared some in my kitchen, and I brought them out and I've laid them out next to each other, and we're going to spot the pattern. So here I'm going to take one example that really shows the pattern in left. So I've got the semantics of in left in 3 different models. This one is model with errors, this one with state, that's read and write from memory, and this one with control, that means read and replace the current stack or continuation. And look how you see this blue stuff. So the blue, okay, I'm only showing you one example in left, but if you look at lots of construct, you'll see that where you get in left in the error semantics, you get s comma something in the state semantics and k of something in the control semantics. And where you see this red stuff in the error, you get the same stuff cropping up correspondingly across the whole semantics. So these show you that there's some, if you like, some things, some actual semantic particle, I like to call them, right? Pretending that we're doing physics. There are these particles of meaning inside in left. In our original in our language, call by value with effects, in left looks like a primitive, but we can actually decomposing it into these other effects, sequencing and returning, that we look at by comparing all of these models. So now we want to form the language, which is called fine-grained call by value, where we bring out sequencing and returning. In fine-grained call by value, we have two separate judgments. Unlike in the original call by value, where value was a special kind of computation, now, a special kind of term, now they're completely separate and disjoint, right? So we have a value, return a value as a computation, and we have sequencing. Not to be confused with let, which is just binding some variables to values. That's all it does, right? So you could have let for two different things, but this is sequencing. So it runs, it's present inside the call by value let, it's present inside call by value application, it's present in many things. That's sequencing. Okay, and I can give you the interpreter. So if you return V, what do? You just return V. And if you want to evaluate sequencing, you first of all evaluate M. If you get a value, you go out. So now a lot of the other stuff becomes simpler, right? Application becomes really simple to evaluate. Pattern match becomes really simple to evaluate because we've taken out all of the sequencing and returning that were previously present, right? So we've just boiled it. The application is just application. Matching is just pattern matching. Nothing more. We don't have to decide whether to evaluate left to right or right to left. That all went into the sequencing. We don't need a CK-VK machine if we're doing a stack semantics, just a CK machine. So all the complication that was present in coarse-grained call by value goes in fine-grained call by value. Okay, so that we've analyzed, this is the first step. We go back to the picture. We've gone down here from call by value, and we've analyzed it into fine-grained call by value. The next step is to analyze these two with, if you like, the really high-level magnifying glass, strong magnifying glass. Okay, so we've finished fine-grained call by value, and the next step is that we've got these models, and we also look at models of call by name, jumbo lambda-calculus with different effects, and we assemble them all together and we analyze. So what's the first thing that we see? We see that in some of the models, the types are very different, like in the models for errors, right? A call by value, again, I've assembled these all in the kitchen. So I'm just giving you a summary here. A call by value type is going to denote a set, but a call by name type is going to denote, remember that there were two errors, crash and bang, right? So a call by name type will denote a set with two designated elements. That's an algebra, if you like. It's a set with two designated elements. So it's a different kind of thing. So in our subsuming language, we must have two disjoint kinds of type, right? Because they're fundamentally different. Call by value type and call by name types are fundamentally different. Okay, now this, I want to show you this because this was literally the most exciting thing. I remember, being a PhD student and talking to other PhD students. We had this whole thing on the board and seeing the kind of this structure. There was also, there were lots of ways you can look at this. There's the categorical side, which I'm not talking about, but here in this picture, you can see it, right? Here's the semantics of call by name plus an arrow, call by value plus an arrow for three different kinds of model. This model is built on a monad, so F would be the free algebra and U would be the carrier of an algebra. These models are for state, so S is the set of states. These models for control, R is the set of, if you like, semantic domain for configurations, the final results, R for results. Okay, look at the pattern. Where you have UT in the monad semantics, you have S arrows in the state semantics and arrows R in the control semantics. And that's true everywhere, right? I had to deliberately arrange these semantics in like these semantics. The state semantics are called by value. I've chosen to arrange it in a way that makes the pattern come out. But no, but it's still cool, right? You've got arrow in these two semantics corresponding to times in this semantics. And you see this pattern everywhere. So you see the particles of meaning. I've color-coded them. These are U and F and arrow and plus cropping up in these models. And this is just analyzing the types. You do the same thing for the judgments, the same thing for the terms, right? You're decomposing everything. And this leads, well, I say it here, similar patterns for judgments and terms, similar correspondences. So now, having analyzed all of this, what we see empirically is this language called by push value. So we have the value types, right here we have the U and the F. So U converts the computation type into a value type, and the computation type vice versa. We can add and multiply value types. We can form function and product types to get computation types. Remember what I said, that we started with jumbo lambda calculus. So we're not just analyzing arrow and times, we're analyzing the whole of jumbo lambda calculus and seeing everything. That guarantees that we're not missing anything, right? It all decomposes into these particles. And if you started with the infinitary version, then that will carry through here. But that depends on your original choice. And now we have the two judgments, a judgment for values coming from the value judgment in fine-grained call by value, and we have a judgment for computation. So basically, a call by value term from the original language became a call by value computation. In the fine-grained language, that becomes a call by push value computation. A call by name term becomes a computation. So computations are the basic translations of the original terms, and we also have the stacks if we started with stacks. And in particular, I should emphasize, every variable in gamma has value type, right? That's how we define typing context. Okay, so let's look at some typing rules. This is the typing rule for a free variable, nothing very exciting. A variable is a value, and here's the binding of, is the let, right? For binding values. V is a value and W, I just give an example of 2. It could be 100, doesn't matter. You can do any number of things. We started with this in jumbo lambda calculus. We're carrying it through. It's present in call by name. It's present in call by value. It looked like this in fine-grained call by value. So this is a binary example of binding. That's the variables. Okay, the F type. If we have a value of type A, returning it, right, a computation in FA, what does it aim to do? It aims to return a value in A. So you see that one works. If M has type FA, then you can sequence it with another term. So this means just as it did before. But the second term N can have any type. This was really based, I should say, before call by push value, there were many similar languages that and some of them that really inspired this. I mean, like there was Andrzej Filiński's language had this kind of generalized binding. And yeah, and I see Brian Howard in the audience. Hi, you had another language with this similar structure coming on. So there are many related languages. I want to these things all influenced the design of call by push value, as well as look-based design. They help me to see this call by push value structure. Okay, plus right. Well, plus just an operation on value. You can in-left a value and you can in-right a value, and you can pattern match. So you pattern match a value, only a value. Importantly, we're only forming computations by case analysis, because that was the only thing that was present in the source language. I'm going to come back to this issue if I have time, which is quite unlikely. Right. So we have a type where that's the F type, the U type. The U type is the type of thunks, right? You take a computation, you thunk it, now it's frozen into a value, you have a thunk, you force it, and you've got a computation. Oh, I just did that one. Okay, so it's not in order. Functions, lambda in application. Yeah, this is the strange thing about call by push value. Functions are computations. That's not the case in fine-grained call by value, but it is the case in call by push value. I'll say more about this. And sometimes we write applications with the operand first. Okay, so we can do CK machine just as we did before. No changes there. That's the CK machine for sequencing. This is the CK machine for application. You want to evaluate an application, you start by evaluating the operator. Let's look at that again. The interesting thing is that you can read this V along, so I call this symbol. You can read this as an instruction to push V, and you can read this as an instruction to pop X. And so we can understand some of the equations, like the beta equation. Look, push V, then pop X, you get, that's just the same as binding X to V. And some of these other equations, like if you print C and then pop, that's the same as pop and then print, right? Because it's not going to make any difference. So what was originally something very strange now makes sense. Suddenly we understand why functions are computations. So here's a summary of the types. This is my slogan: a value is, a computation does. So you see that you see that you have all of this structure going on. Sorry, value is, you see, a value is a thunk, a value is a pair, a value is a pair. A computation aims to return, a computation aims to pop and then behave. So you see the difference between values and computations. Here's a, I don't really have time, but I just very quickly, what does this example do? How quickly can I go through this? Prints hello 0. This is, oh gosh, there's a typo in here. No, there isn't. Sorry, you make these two bindings. X is 3 and Y is this thunk. You print hello 2. You start work on this first part. You print hello 3. You push 7 onto the stack. You print we just push 7. You force Y, which was this thunk. You print hello 1. You pop Z. You print we just pop Z. I can remember 7, right? We press pop 7. You're going to return 10. And then your W is therefore bound to 10. So you print W is bound to 10, you return 15. This returns a natural number, so its type is fnat, but it's cheating because I've put in all this arithmetic, which is not part of call by push value, because we're putting together values which we're not really allowed to do. So it's good for the example, but it's not really call by push value. Okay, that's the end of the second part of the talk. We all now know what call by push value is and how it arises. So in the last part of the talk, I don't know, I should probably allow 10 minutes for questions or something like that. So, but anyway, that's hopefully we have some time to go through these. I want to look at some variations, slight variations that actually people sometimes do or people suggest to me. And then I either want to kind of slag them off as a propaganda tool, but also they have some advantages, right? So here's the first one. I used to be a fan of this, and I am, years ago, but I kind of turned against it. So if you remember, long ago in the talk, I gave you the syntax of call by value values. So here's an example of what I call a complex value. If true, then 3, else 4. That's not a value because it needs to be evaluated. So we don't allow that. Call by push value doesn't allow that in the typing judgment, and the same for fine grain call by value, something like that. So should we add them into the syntax? Should we allow pattern matching into values? Well, on the one hand, if you look at if you think very only denotationally, then you're likely to think this should be done, right? Because it is present in all the models. But the main thing is that my main argument against it is it doesn't appear in the original call by value terms. So I'm saying we have obtained call by push value just by analyzing call by name and call by value and seeing what's there. Nothing else. So anything which didn't appear in the semantics of call by value terms, I don't want to put in. Another problem is that it changes the operational character of the language. So it's true that you can still give an operational semantics to a language with complex values, but we don't want to give an operational semantics. We want call by push value to just naturally have an operational semantics without us needing to do anything. And you have to make, if you put these into the language, you have to start deciding what order you're going to evaluate the values, and it kind of completely changes the operational character of the language. And finally, the other point I want to make about complex values is it doesn't really work well with recursive types. So let me just tell you why. I should say, if you are going to add this, then you can even take it further. You can add lots more. You can add higher order value types, for example. I mean, you can go in this direction and add lots of stuff. It's possible. You can do it. You can extend the operational semantics and make it work. What's the problem with type recursion? Let me just explain. So here's an example of a value type, a recursive value type, if you've got type recursion in your language, which is empty. So it should be isomorphic to the empty, to 0 type. Well, if you're allowing people to pattern match values of type 0, which you will if you allow complex values, you want to do the same for this recursive type. So then you should have a value of this type. But you're going to have a value going from 0 times 0 to 0 with complex values. Why not from this to this? But there's no obvious syntax that makes this work. So so this is just turned me off complex values completely. Okay. Second variation would be to erase one of the type constructors. So if you remember, the two value types and computation types are disjoint classes of types. So it's possible to erase one of them. So if you erase F, then the value types will be a subclass of the computation types. If you erase, I should say subkind, shouldn't I? A subkind of computation types. If you erase U, then computation types will be a subkind of value types. And this won't cause any problem because of this isomorphism that times commutes with U, product commutes with U. You even could erase the distinction between the two kinds of products. You could take it a step further. And why would you want to do this? Well, one reason is that there are some models in which F is invisible, and there are other models in which U is invisible. For example, if you're thinking of domain, CPO semantics, domain semantics, in the computation types are pointed CPOs with the least element, and the value types are general CPOs. So in that case, you might say, you just think about that model, you might say that U is invisible. Or if you're looking at one of these models, you'll say F is invisible. And but the point is, we want call by push value to capture all of the models, so we keep the. So I would argue that it's F and U should both be present. Okay, so that's another variation. The next one, this one, I'm a little bit sympathetic to this one, right? This is coarse-grain call by push value. So just as we have this distinction between call by value where you only have computations and fine-grain where you have two separate judgments, you could do the same. And the problem with fine-grain is that this value judgment is really only an auxiliary role, only has an auxiliary role. So any theorem that you have, usually you will find that it's only true for the computation judgment. Like saying everything in the model is definable or every computable element is definable. That kind of theorem will be true for the computation judgment. So you could say, let's do the same for coarse-grain call by value. Let's have no values and let's represent a value as a computation of F type. If you do that, return will disappear from the syntax. You might also choose to erase F. I mean, technically it's separate, but it's a natural combination of changes. But the problem is that some denotational models become more complicated. Not all, but some become more complicated. And we're going to go back to the CK-VK machine, and we're going to go back to needing to decide whether it's left to right or right to left. Now, I should say, if the effects that you're studying are commutative, so it doesn't matter what effect, like if you make two non-deterministic choices, it doesn't matter what order you make them, then that isn't a problem. So I would say this is quite natural if you're studying commutative effects, but if you're studying non-commutative effects, it might be, I'd say it's a bit unnatural. Okay, that's I'm just really sounding off and giving my opinion on different variations. Variation 4, okay? So the previous one was trying to get rid of the value judgment. This one says, let's get rid of the computation judgment. So let's just, again, let's think about fine-grain call by value. That has two judgments, the value judgment, computation judgment. It's possible to get rid of the computation judgment and represent a computation as a value of thunked type, right? So you're erasing the distinction between a computation and a thunk. And this is, examples of languages that do this would be the monadic meta language, and of course Haskell is based the way that, I mean, when I say Haskell, this is a bit questionable because of all the issues with divergence and exceptions in Haskell. But roughly speaking, it follows the pattern of the monadic meta language. You can do the same with call by push value. You can get rid of the computation judgment and just use values of thunk type. If you do this, thunk and force disappear from the syntax. You might also choose to erase U. It's a natural combination of changes. This is quite suitable if you're only thinking about models that come from monads and algebras, because in those models, thunk and force are indeed invisible. But there again, there are other models. I mean, the cell generation model is the clearest example where things become more complicated if you get rid of thunk and force, right? So some models are more complicated, but some models, it's fine. So we could get rid of the computation judgment, or we could get rid of the value type, the value judgment. Okay, now, completely different kind of variation. So if you think about a closed value in call by push value, here's an example of a closed value. It's built up from thunks and tags, right? You see the tags in left and in right. So every closed value is built up that way. And there's a similar fact that you can formulate for stat. So you can break this down. I call this part with the in lefts, I call this the ultimate pattern, and the thunks are the filling, right? So you could take a version of call by push value which gets rid of the stack. So it has no sum type of value types and no product of computation type. It incorporates them into U and F, the sum and the product, right? So that gets rid of the tags. So if you think about it, oh, what's going on here? Sorry. If you think about it, so every call by push value computation is now going to compile into a family of computation. So although this is a smaller language, you can compile down into it, but you're getting families of terms, families of types and families of terms. Everything compiles into a family. And this corresponds to a categorical construction that's often been used, especially in game semantics, for building models. So this, for studying these particular models, this is an interesting language to use. Right, so I think that the message that I keep saying is that these different versions are all interesting for specific models, but the thing about call by push value is that it works for all the models rather than specific kinds of models. Okay, version 6. This is a slightly different story. Remember that we asked for the most general leftist and rightist connective. Well, we can do this in call by push value. We can say, what is the most general leftist connective giving a value type? Surprise, it's sum of product. If it's giving a computation type, it's f of sum of product. For rightist connective, giving a computation type, it's product of multi-array function type. If it gives a value type, it's u of that. So these are the most general leftist and rightist connectives. So that gives you jumbo call by push value. So that's on the downside, that's more complicated than ordinary call by push value. But I often like to use this sort of in thinking about things because it helps me to see the big picture. There's 4 real type constructors going on. Right, and it also has the advantage that this is now quite close to call by value and call by name. If I work with jumbo call by push value, then to go from what I've done to a theorem about call by value jumbo lambda calculus or call by name jumbo lambda calculus, there's nothing to do because it's immediately there. There's no decomposition anymore. So the whole story about fine grain analysis, all of that thing that I was telling you, doesn't apply here. There's no fine grain analysis. We've kept everything. But we still synthesized call by value and call by name in jumbo call by push value. So I think this is an interesting language to me. This is, of all the variations, this is my favorite. Okay, the last one is the core of call by push value. So in the core, we have this jumbo connective that involves f, and we have this jumbo connective that involves u. These are the ones that do the hard work, if you like. These are where the interesting stuff happens. These two are just the boring bookkeeping connectives. So if we get rid of these, we get what I call the core of call by push value. We include these two and we exclude those. And then we can we can compile tag free down into this core. So although it's a smaller language than tag free, everything from the whole of the language can be compiled down into it. And it's contained within all the subsystems that we've seen, because every type is, if it's a value type, it's actually call by value. If it's computation, it's f of call by value. Every type is either call by name or u of call by name, and every type is tag free. So this is literally within the intersection of, if you like, you think of this as the intersection of call by value and call by name. That's approximately what this is. Call by value and call by name are subsystems of call by push value, and this is the intersection. And if you like, this is, if you really want, let's say you're trying to prove some theorem of operational semantics, I don't know, applicative by similarity as a congruence, whatever it might be, and you just want to get rid of all the tedious bookkeeping and focus on the hard stuff, you might choose to think about the core, right? So it focuses on the difficulty. Okay, so let me summarize. So we've said, this is the basic propaganda point that I've been making for quite a long time, that call by push value gives you the fine-grained structure of a wide range of models. I mean, that includes operational and denotational semantics. It's all there. And the other systems, they don't achieve that directly, but they are mutually translatable with call by push value. So they're not hugely different, right? I mean, they're just not, they don't directly correspond to the structure of the operational and denotational semantics. The one which does really apply to all the models is jumbo call by push value. That does describe, all the models, but instead of being fine grain, it uses jumbo connectives. The other systems, you can use them if for specific denotational models or operational purposes, right? Depending on what you want to do, you could make these changes, and that's fine if you just want to focus on that particular thing. But if you want to sort of this big picture view across all the different models, then I would definitely encourage you to use called by push value. So okay, so it's a bit of a propaganda talk, but okay, I like doing propaganda. And so you hopefully have seen both the basic story of call by push value and also some of the variants and what we learn by thinking about them. And I think I found it really helpful to think about all these variants over the years, and gives me different perspectives on aspects of call by push value. And that's it.
Well, thank you very much, Paul, for a very entertaining talk. Yeah, I think applause is difficult in this setting, right? But there are a couple of questions, and I think we can basically just open a discussion after that. We have some time. So I know Max had some questions. Max New, do you want to ask them?
Sure. Hi, Paul.
Hi.
Oh yeah, so I had a question, which is, do you have a reference for this tag-free call by push value? I'd never seen it before.
No, but in some of my papers, maybe the adjunction semantics of call by push value, I think I use the word pre-families, which is a terrible word. So that a pre-families model of call by push value or something like that, which is basically in the chat. So it's that's tag-free would have been a better name. So I didn't make it into a language, but you can see the structure. And it was exactly because I wanted to talk about game semantics, and they were built from a families construction. So I wanted to have the basic structure that I apply the families construction to, and that would be a model of tag-free call by push value.
Okay. Yeah, I think maybe I can work it out by looking at it a bit closer. And my other thing was, you mentioned having a commutative effect in call by push value, and at that point, aren't you getting closer to something like linear logic? If it's a commutative effect, it's kind of like there's this enrich effect calculus, which is like the generalization of call by push value to throw in all the connectives that ruin the operational semantics, and then if it's commutative, then you would get linear logic. Linear nonlinear logic would be the analog of that, right?
Yes. There's actually two different I mean, that's one line of work, which is a sort of linear development of call by push value, if you like. And then there's the other line, which is sort of Erhard and Tasson and Pagani and other people, which is slightly different. So in the one case, yeah, but yes, hang on. So if we go back to the complex value, all I said, I alluded to it I said that if you add in complex values to call by push value, you can then start to go further and add in other extensions like the arrow, like arrow on value types. And you can also, that would include the copower type, the product of computation types, the product of value types, and the sum of computation types. So all of these things can be, and they can be added in, and the lolly type as well. So you get lots of extra type constructors are possible. All of these exist in some models, not all models. Although every model can be embedded, this was all the paper of Simpson and Milberg and Egger, that every model can be embedded in models that have this additional structure, fully faithfully. If the effects are commutative, then indeed you can go further into linear, nonlinear logic, which is the version of linear logic which is closest to this whole call by push value story.
Yeah.
Right, and so yes, that's true. And also the work that I mentioned, the other side of linear logic with Erhard and Tasman, their work, that was also primarily working with commutative effects.
Yeah.
So yes, so both, whichever linear logic connection you're looking at, it definitely is particularly appropriate for commutative effects. I mean, I said here this business where you had coarse-grain called by push value, you can consider that without commutative effects. It just means you have to make some specific decisions. In the commutative case, you've got you don't have to make any decisions. So it's particularly natural in that instance. And this one is quite similar to what they did. Right?
Okay.
The coarse-grain version.
Okay,
Yeah.
that was my question. Thank you.
Okay, thanks, Max. And I think there was another quite pertinent question from Ilan.
Yeah, I had a question back in the start. And the question is, in what sense are we considering generality in the leftist and rightist formulations? You said it's like the most general form of it, but in what sense? If they are equivalent, like.
So that was in the context of the jumbo version of call by value and call by name, right?
Yeah, yeah.
Okay. So you're asking, when I claimed that these were the most general leftist and rightist connective, what does that mean? Is that what you're... So essentially, so I have it's explained. So I have a paper on jumbo lambda calculus from iCal 20 something 2000 I don't know 7 or something, and so I mentioned that these reversible rules have to have this naturality condition, which I kind of didn't really go into. So this has to be natural in gamma, and this one has to be natural in gamma and C varying over gamma. We have to be a bit careful with naturality there. With these conditions, you can show that these, it's not terribly precise, but if you think what the most general form of a reversible rule, let's say on the left, you're going to have something appearing in red on the left of the turnstile. You're going to have a family of premises. Each premise will have several extra variables, a list of extra variables. That gives you your family of lists of types. And then, so therefore that new type that will have that reversible rule will be equivalent, will be isomorphic because of a Yoneда argument and all the naturality that's going around, will be isomorphic to the variant tuple type. So it's a Yoneda via a Yoneda argument, these are the most general leftist and rightist connectives. Of course, that argument is based on beta eta, assuming beta eta, so it's kind of ironic. We find the most we define the whole concept of a leftist connective is that it has a leftist reversible rule, assuming beta eta. Our whole exploration of what is the most general leftist and rightist connective works on the assumption of beta eta, but then in the end we throw all beta eta away because we're adding effects, and that's when it really matters, right? Does that answer your question?
Yeah, I'll be happy if you'll give a reference later.
Okay, so yeah, just a paper called Jumbo Lambda Calculus.
Cool. Thanks.
Oh, and I think William just linked it in the chat, so you have your reference right now. And I think there was also another question from Dimitri, if you'd like to ask it. Or maybe I can just read it out. So Dimitri asks about the explanation of call by push value. So the question is, can we explain call by push value only in terms of call by value and call by name before explaining various effects? So,
well, for me, the motivation comes from the analysis of call by value and call by name. Because you can certainly define it just pull it out of a hat and say, here is a language. But it doesn't really explain why. That said, other people have, the closest thing I can find of a completely different story, which ends up somewhere similar, is the whole analysis of proof search using focusing, which has some relationship. I don't want to say they're the same. I wouldn't say that, but it has some relationship, particularly when you take into account all of this ultimate pattern matching. At least, it is the case that one of the papers on focusing, namely the Harper, Licata, Zalberger, had a system where the syntax of types was the same as call by push value. The terms were not, but the types were. So that's one point of connection, right? So that was an analysis that led to something closely related. That's the only example I can think of where you would motivate. Well, you can also, there's a categorical semantics of call by push value, roughly speaking, using adjunctions. That's a bit of a simplistic thing to say. But roughly speaking, a model of call-by-push value is an adjunction. And a lot of these adjunctions are things that people studied and are interested in without thinking about call-by-value and call-by-name, right? So some of the categorical structure, again, people might study without thinking about call-by-push, without thinking about effects and evaluation at all. They might be looking at in a completely different setting, and yet some of the same structure comes up. So there are points of connection with different stories that don't talk about call-by-value and call-by-name, or don't even talk about effects at all. Yeah.
Okay. I also have a question if there's no one else wanting to ask one. So I've started looking at the questions of dependent types and evaluation or end effects. And one thing that strikes me as connected to some of the stuff that you talked about there in today's talk is this notion of complex values. Because quite often when you see papers attempting to combine effects and dependent types, you basically have a variant of pure evaluation tied to conversion. So basically you only parameterize with values, and then you need complex values in order to have meaningful conversion in your dependent types. So do you have any ideas about thinking about doing something with dependent types and call-by-push value?
Well, okay, I can say several things on that. First of all, there have been several papers by different people on dependent types and call-by-push value in the last few years, taking different, in some cases related approaches to this issue. There is a basic problem that it doesn't seem possible to extend call-by-push value to a dependently typed system in such a way that that the translations from jumbo lambda calculus, the call-by-name and call-by-value translations, extend to translations from dependently typed systems. So I would say, I mean, I don't know if in the literature there's a distinction between dependent types and index types. Like some people write, I can't remember the name of the system, but there's some system people have worked on which has only index types. So it's like you have these separate kind of sort of if you like a level 0 type, which basically ranges over countable sets, natural numbers, something like that. Booleans, and then you're allowed types to depend on those, but nothing more than that. And that, I think, fits very well with call-by-push value. I mean, I remember reading that and thinking, well, it's very similar. I mean, you saw this. I'm always writing about sums, particularly here, right? I mean, I don't really think about a sum over natural, types depending on natural numbers. I don't think of them as dependently typed. I know I always laugh when I hear people give an example of dependent type, and the first thing they come up with is vectors of different lengths. I'm like, that's not a dependent type. That's just an index type. So here, so something like that is certainly compatible with call-by-push value and will be fit with the translations from call-by-name and call-by-value lambda calculus. But if you really want dependent types, then, I mean, you have to do something more fancy. I mean, I don't know in detail all the work that's been done in the last few years in that area, but definitely people have been working in that, and there have been quite a few papers.
Sure. Okay. So I think we have about 5 minutes till the first contributed talk. So I'd like to thank Paul again, and let's just take a quick break and reconvene in 5 minutes, and we'll start with the contributed talks then.